Here we'll look at a few properties of our definite integrals. Our first is if we integrate a number m through the interval a to b, the result be m times b minus a. In the idea, if we have some interval from a to b, and we have a constant function that occurs at m, the area underneath is simply going to be a rectangle. The height of the rectangle is m, and then the length would be b minus a. So we can easily compute this area. The next property, let's suppose our function is greater than or equal to some value m over the interval a to b. Then we would have the definite integral from a to b of f of t dt is greater than or equal to m times b minus a. So if our function is bigger than a constant value m, the area will be bigger than the area of that rectangle. Next, we'll suppose our function is always smaller than some value capital M. In this case, the integral from a to b of f of t dt will be less than or equal to the rectangle between b and a that goes to m. So now we have this rectangle. Our function is always smaller than m, so the area under that curve will be smaller than the rectangle. Our next property, if we have the integral from a to b times beta f of t dt, where beta is some number, then we can actually pull out the constant beta. So if we multiply the function by a constant, I can move it in or out of the integral. Next, let's suppose we have two functions, g and f. Then if I take the integral from a to b of g of t dt, it will always be less than or equal to the integral from a to b of f of t dt. Our next property states that if we take the absolute value of the integral from a to b of f of t dt, this will always be less than or equal to the integral from a to b of the absolute value of f of t dt. So we can't just move an absolute value in or outside of an integral. It actually makes it an inequality rather than an equal. The next property says if I have the integral from a to b of f of t either plus or minus g of t dt, so if I either add or subtract two functions, this is equal to the integral from a to b of f of t dt plus or minus the integral from a to b of g of t dt. So essentially, what this says is that I can break up my integral along either addition or subtraction. The next property, if I have the integral from a to b of f of t dt, and I add the integral from b to c of f of t dt, then this is equal to the integral from a to c of f of t dt, which tells me that as long as the upper limit on the first is the same as the lower limit on the second, I can actually combine this to one big integral. Our last property states that the integral from b to a of f of t dt is equal to negative integral from a to b of f of t dt. So actually switching our bounds changes the sign of the integral.